Hey, College Math, welcome back. Here is section 6.2, a very special section because it is not just about trees, but it's also our last section of the semester. We're done after this. Woo! Um, yeah, but trees, 6.2. Our objectives are to identify properties and examples of trees, and then define a minimum spanning tree, and then use Kruskal's algorithm to find minimum spanning trees in a given graph. Okay. So this is kind of why I moved 6.2 to the end, because it felt kind of weird to go to this and then back to circuits and paths with 6.3 and 4. So starting off, a tree is a connected graph that has no circuits. Okay, so it's a type of graph and it has those conditions, right? And so there's three properties that kind of help us to make sure that this is true. So the properties are every pair of vertices is joined by a path, every edge is a bridge, and then if there are n vertices, there are n minus 1 edges. So these are the properties we can use to look at a graph and say, okay, yeah, that's a tree, or oh no, it doesn't really follow this rule. It's not a tree. Okay. So let's go ahead and just identify a few of them. Okay. So tell whether the following graphs are examples of trees. So looking at this first one right here, I notice a few things with there's 1, 2, 3, 4, 5, 6, 7 vertices and 1, 2, 3, 4, 5, 6 edges. So it kind of matches with property 3. Every edge is a bridge, yes, because if I take any one of these edges out, I'll end up with an isolated vertex. And so that will disconnect my graph. And that's what a bridge is, right? If I take the edge out and it disconnects the graph, then it's a bridge. And then every pair of vertices is joined by a path. So every single pair that I can think of vertices, there is a path between those two vertices, right? So if I think of, for example, like this vertex and this vertex, the path that takes me there is this path right here, right? And so this is definitely a tree. And then the last thing is that, there's no circuits. There's definitely no circuits here because there's no way I can, for example, start at this vertex, leave it, and then be able to get back to that vertex without using the same edge, right? There's no way I would have to go back and use the same edge, and I can't do that in a circuit. All right. So this one is a tree. This one is a tree. What about this next one right here? Well, without even using the properties, we can kind of immediately tell that this is not a tree. And the thing that kind of gives it away is the fact that there is, if you haven't already been able to tell, there's a little circuit right here. Okay, I can actually kind of start at this vertex and follow along and end up at the same vertex that I started at, right? So that definitely can't be a tree, and it kind of violates a few other properties as well. Okay, so specifically it violates the second one, every edge is a bridge. If I get rid of this edge right here, my graph is still connected, right? So not every edge in this case is a bridge. All right, and then the next one is that if there are n vertices, then there are n minus 1 edges. Let's check that one. 1, 2, 3, 4, 5, 6, 7, 8 vertices. 1, 2, 3, 4, 5, 6, 7, 8 edges. So there's supposed to be 7 edges if this was an actual tree. Okay, so not a tree for a few reasons, right? There's a circuit, not every edge is a bridge, and then there are the same number of vertices as there are edges when there should be one less, okay? And then this last one over here, we can kind of check every single one. Is there a path? The first one's a little hard to check sometimes, and so we kind of rely on the others. We don't see any circuits here. Every edge is a bridge here because no matter where I kind of get rid of an edge, it's always going to disconnect the graph. And there are 1, 2, 3, 4, 5, 6, 7, 8 edges, or sorry, vertices. 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7 edges. 8 vertices, 7 edges. So that works. And then I can get from one vertex to the other by following a path, right? No matter which two vertices I choose, there's always going to be a nice path between them, right? And then we also just don't see any circuits. So this one is also a tree. Okay, so those are a few examples and non-examples of trees. Okay, so we can have trees that are their own graph, like the ones we saw here in A and C, but we can also find a tree within a bigger graph. I can actually look at this graph right here and find a tree. I could pretty much just highlight every single edge except maybe like this one right here, and that would be a tree within this graph, right? Even though this graph itself is not a tree, we can find one within it, right? And so the idea is that specifically we want to find what's called a minimum spanning tree in a weighted graph, okay? And this is kind of going to get at the idea pretty similar to how we found those Hamilton circuits using nearest neighbor and cheapest link algorithms, how we found those circuits within a bigger graph, but I wanted a minimum weight circuit. Here it's kind of the same thing. Instead of a circuit, I want to find a tree that has minimum weight, okay? So that's kind of what a minimum spanning tree is. It's a tree within a weighted graph that spans all the vertices and has the least weight. Okay, when I see the word spans, okay, that's just kind of a fancy word for connects or includes, right? So that just means that the tree that I find involves all of the vertices. Okay, the tree, if there's a graph with 6 vertices, the tree that I want, the minimum spanning tree, is going to have 6 vertices, all 6 of the vertices of that graph. Okay, so for example, if I look at this graph right here, if you kind of analyze it for a bit, if you kind of just take some time with it, you'll see that a good minimum spanning tree involves this edge, this edge, this edge, and this edge right here, right? And so I'm going to draw it a little bit nicer. I'll just do it this way. So this, this, and this. So that is your minimum spanning tree right there. Okay, it's a tree. You can kind of check for yourself, right? There's 1, 2, 3, 4, 5 vertices, 1, 2, 3, 4 edges. There's a path between every pair of vertices, and then every single edge is a bridge. And then we clearly don't see any circuits within the purple, right? There's a circuit in the graph here, right? One good example of a circuit would be A, B, D, E, but I don't include that DE edge. So there's no circuit in the purple, which is this tree. Okay, so the minimum spanning tree for a graph like this would be AE, AB, BC, oops, and then CD. Okay, that would be my minimum spanning tree there. Okay, it's minimum because it takes up the least weight. It's spanning because I included all the vertices, and then we already checked that it was a tree. Okay. Now, it won't always be easy to find a minimum spanning tree just by looking at the graph and picking edges, right? So we can rely on what's called Kruskal's algorithm. It's used to find the minimum spanning tree in a graph. And Kruskal's, unlike nearest neighbor and cheapest link that gives us a circuit of small weight, it's not guaranteed to give us the minimum weight, but it gives us pretty close to it, right? This one, this algorithm is guaranteed to give us the smallest spanning tree, the spanning tree that has the smallest weight. Okay, so let's see what the steps are. All right, our first step is we're going to find and mark the smallest weighted edge. If there are multiple edges that have the smallest weight, we're going to pick our favorite. Okay, so if I have multiple edges, for example, if my smallest weight was 2, and there are multiple edges that had 2, then I would just pick whichever one to start with, right? Find and mark the next smallest weighted edge, including if it was the same weight. So for example, if I picked an edge with a 2, I'm still going to look at all the other ones that have a 2. And if there are no more 2s, then I would bump up to the next smallest one, right? Same case, pick your favorite again if there are multiple. We're going to repeat this until we create a tree that spans all the vertices while making sure we don't create a circuit. Okay, so when we're choosing those small weight edges, make sure you're not creating a circuit by accident, okay? And the way we want to answer this, the kind of our response to like what the minimum spanning tree is, after we kind of drew it on the graph itself, we want to go ahead and write out the sequence of edges that we chose them in that order, okay? Let's go ahead and try this. All right, so in this graph that got a little bugged out, give me 1 second to fix this. There we go. Okay, sorry. I don't know what happened, but it's all good there now. Okay, so we're gonna find the minimum spanning tree of the graphs below using the algorithm, and we're gonna identify the total weight of each minimum spanning tree we find, right? So here's the first graph that we're gonna find a minimum spanning tree for. So the idea is we're going to look for the edge that has the smallest weight. Okay, we're looking and we see that that's going to be this edge right here, BC. So I'm going to mark it because it's going to become part of my spanning tree. And I'm going to write the edge that I just chose. So BC is the first one I selected. Then I want to look for the next smallest weight. Okay, so it looks like I have 6. Okay, so the first two are never going to break the rule of, don't form a circuit. So you can always choose the first two without worrying about anything, right? So BC, AC was the next one I chose. Now here's where we need to make sure we're paying attention and not creating a circuit on accident, okay? So choose the next smallest one. Here it looks like it is 4, 6, 7, so CE right here. Okay, CE. And then I have an 8 right over here. I'm not closing any circuits, right? Nope, I'm good. So then BD. Okay, so then the next biggest one is 12. Now notice I have 2 options here, 12 and 12. Typically, the thing says pick your favorite. This one right here, CD, can't be our favorite because if I did choose this one, I'm creating a circuit, which means I no longer have a tree. So I can't choose CD. So that means I have no other option but to choose FE. Now, sometimes you might come across a case where you actually can't choose either. There's 2 12s and they both create a circuit. That means you're just going to move on to the next smallest weight. So then I would, in that case, if that was the issue here, I would move on to the 13. But it's not an issue, so I'm good. So then EF was the next one I chose. And then you would actually keep going, but realize, look, I have created a tree that is spanning all the vertices. I'm using all the vertices. So I'm actually done. I don't need to even check this 13 or this 23. All right, so here is the minimum spanning tree. Okay, this is the picture, and then this is the list of vertices that we chose in the order that we chose them, right, based on the algorithm. And then I want to find the total weight. So what's my weight here? Well, BC was 4 plus AC was 6 plus CE was 7 plus BD was 8 plus EF was 12. Okay, so we add that up and we're going to get 37 is our total weight for this minimum spanning tree. Okay, hopefully it doesn't sound too bad so far. Let's try one more. Okay, so here's a little bit of a more complicated graph. Let's give it a shot. So what do we see? We see that I forgot to include an edge. I'm looking at the one I have on my paper. There should be an edge right here. Okay, give me 1 second to fix this. Okay, this weight, this one right here should be a 1. It's gonna do that. This should be normal. And then this one should be a 2. There we go. That fixes that. Okay, so now let's go ahead and find our minimum spanning tree. So let's start with the smallest weight, which is the one I just threw in, right? So here is our first edge we're going to include. So DE. Okay, then I look for the next smallest, which is this 2 right here. So this is our next. Okay, so DG. All right, and so now I move on to the next smallest, which is 3, and I have multiple that are a weight of 3. Okay, so let's kind of look through. Can I choose this one right here? Yes, I'm not going to close, or I'm not going to create a circuit if I choose this one. So GH. If I look at EG, I can't choose that one because I will create a circuit there, so I'm not going to choose that one. CD, that one's a good one to pick because it's not going to create a circuit, so CD. Okay, and then CF, same. I'm not making a circuit, so I can pick that one with no worries, so CF. All right, now I move on to the 4s. Okay, so I have multiple 4s here. If you kind of take a look at it for a few seconds, you're actually going to find that you can pick whichever one you want to start off with. But then every single one after that is going to create a circuit because of the fact that they're all connected to B, right? And so then from there, whichever one we choose after that's going to create a circuit. So from here, let's just pick our favorite and then we won't be able to pick any of the other ones, right? So let's go ahead and pick, I don't know, BF. Okay, so I'm going to choose BF. Okay, so here's an example where everyone's spanning tree that you like, if I gave you this one to try on your own, a lot of people's spanning tree would look different, but it might still be the correct answer, right? However, and so I kind of said, I told you at the beginning that you would be able to find the right answer. In this case, there are multiple right answers, right? There's going to be a bunch of different minimum spanning trees that have the same weight because they're all 4 right here, right? Even though I can pick different ones, they all have a weight of 4. So our final weight will still be the same. All right, and so then the next smallest is 5. And if I choose this one, I don't have any issues. Okay, no circuits being created there. So I chose AH. And then I'm done here because now I have spanned all the vertices. All the vertices are included. And it's a tree. Okay, so I found my minimum spanning tree. There's my list of edges that I chose. Now I need to add up their weights. So I have DE was a weight of 1, plus DG was a weight of 2. GH was a weight of 3. CD, 3. CF, 3. BF, 4, and then AH, 5. Okay, this ends up having a total weight of 6, 9, 12, 21 is our total weight. Okay, and there we go, minimum spanning trees. All right, and so this is kind of a really good application in a lot of maybe like city planning, especially when you're thinking of the cables that kind of run underneath us that connect our phone lines and our internets and all that fiber optic cabling stuff. That stuff is pretty expensive. And so it's not always wise to create a circuit, right? We don't really need to create a circuit among, like if I imagine each of these vertices was like a city or like a house, I don't really necessarily need a circuit. And if I think about it, a circuit would actually cost more money because I'm including more pieces than I need. A minimum spanning tree would be a lot more efficient because I'm connecting all of these houses. Maybe they need to be connected in order for the internet coverage or the speed to be the best they can be. They all need to be connected together somehow. And so this is one way to connect them, but without kind of including the extra step of having to go back home, like connect circuit, like connect back to each other. And so that's kind of another application of this whole graph theory stuff, right? Cool. Well, chapter 6 is coming to a close. The semester's coming to a close. After this, we'll have a project on this chapter and then review. Okay. So hopefully this sounds good, you guys. Let me know if you have any questions. Okay. Have a good rest of your day.